One slow dependency can poison an entire cloud system, and most teams don't even see it happening until healthy services start failing right along with it. They blame the traffic, they blame the code, they even blame the cloud bill. But the first thing that actually broke was the model, because the system treated every remote call like it was cheap, safe, and guaranteed to return on time. That assumption never survives real pressure. In a .NET microservice chain, delay spreads fast. A slow call holds onto threads, it holds onto sockets, and it eventually triggers a wave of retries. Queues start filling up while pools start draining. On the dashboard, the services still look like they are up, but the actual capacity is already disappearing underneath them. This is exactly why this topic matters, because the failure doesn't start with a crash. It starts with waiting. So in this episode, we're going to strip this down to the real mechanics. We aren't talking about basic error handling or looking at happy path diagrams. We are talking about failure containment. This is about how to stop one sick service from dragging the rest of your platform down into the dirt with it. Silent latency is the real toxin. Most teams are still designing their systems around an old model. A service calls another service, it gets an answer, and then it moves on. Maybe there is a timeout or a retry involved, but the call itself is treated like a small detail in the request flow. It feels almost like a local method call with a little bit of network tax added on top. And that's where things break, because a remote dependency isn't just code you don't own. It represents shared time, shared capacity, and shared risk. To see how this works, picture a very normal path in a .NET system. A user signs in, and your API needs a token check or a profile lookup from an identity service. That identity provider doesn't go fully down, but it just starts getting slower. It isn't dead, it's just late. And in a distributed system, being late is enough to cause a disaster. Your API request now waits longer on that outbound HTTP call, and while it waits, that request hasn't disappeared. It is still consuming resources inside the app. The incoming request pipeline stays busy longer, the outbound connection stays occupied, and upstream callers have to wait longer for your API to respond. If that API also needs to do database work after the IUth completes, that database activity starts later and piles into the next wave of incoming requests. Nothing looks dramatic yet, but the system is quietly filling up with stuck work. This is the part most people miss. Outages get everyone's attention, but slowness is something people tend to tolerate. In distributed systems, slowness often does more damage because it has time to spread before anyone can react. A hard failure gets rejected immediately, but a slow failure gets admitted into the system and then multiplied across the entire path. In ASP.NET, even when you use async code, waiting still costs you something. You are holding on to the request state and tying up connection lifetimes, which extends how long each unit of work lives inside the service. Once enough requests do that at the same time, your throughput drops even if the CPU still looks calm. That's why teams get so confused. The service appears to be online, the health checks pass, and the dashboard isn't screaming, but your useful capacity is gone because too much work is trapped in a waiting state. And the problem never stops at just one service. The service calling identity slows down. So every caller above it starts to slow down too. Maybe a gateway keeps connections open, or another API waits for the first one before it can even build a response. A background worker might depend on that same identity system for token acquisition, and now it processes fewer messages per minute. Queues begin to grow, not because your demand exploded, but because your completion rate slowed down. That is a very different problem to solve. Adding more replicas might help for a minute, but if every new replica waits on the same slow dependency, you've just expanded the size of the waiting room. The result is that the cloud looks busy, but it isn't being productive. This matters at the leadership level too, because teams often read the situation as an application bug or a failure to scale. In reality, it can be neither. You can have perfectly clean code, plenty of nodes, and a solid cloud spend, and you will still lose the system because your architecture allowed one dependency to hold everyone else hostage. That isn't a coding issue, that is a capacity illusion. I've seen this pattern happen during very ordinary morning loads. Nothing dramatic was happening, but users logged in, traffic rose, and an auth dependency started lagging. Suddenly, services that don't even own authentication began to stall because they all depend on something that does. Support tickets started arriving from completely different parts of the platform. The outage looked wide, but the root cause was actually very small. That's why these incidents confuse people so much. And once that latency starts spreading like that, many teams end up triggering the next wave of damage themselves. Why retries turn instability into a self-inflicted attack. When a team sees a failed call, their first instinct is almost always to try again. It feels like the responsible thing to do, and in a single isolated process, it usually works. But in a distributed system, the math changes completely. Every retry you send is just more traffic aimed at a service that already proved it couldn't handle the first request. That instinct comes from an older, simpler way of thinking. You assume a packet dropped or a tiny network blip happened, and a second attempt will clear it up. That's fine for minor hiccups. But here's the problem. Overload isn't a hiccup. If a downstream service is already saturated, your retry doesn't fix anything. It just adds another request to an overflowing backlog, then another, and then another. you aren't helping the dependency recover. You are actually increasing the pressure while it's already losing control. I started seeing this differently when I stopped looking at retries as safety logic and started seeing them as load generation. One failed call with 2 extra attempts isn't just one failure. Across a single user journey, that might turn into 3 outbound requests. When you look at a whole service fleet under pressure, that pattern creates waves of duplicate demand that all chase the same limited capacity. Because most of your clients probably share the same retry policy, they all fire on the same schedule. They line up, they surge together, and they hit your weakest point all at once. In the .NET ecosystem, this gets dangerous fast because the tools make retries so easy to set up that you often forget they exist. You register an HTTP client, you attach a resilience policy, and you feel like you're covered. But if that policy retries on timeouts or broad exceptions while keeping a long timeout window, you have essentially built a pressure multiplier. The call lasts longer, the sockets stay busy, and the upstream request lives longer. Then the retry kicks in and extends that whole chain even further. The nasty part is that this actually looks smart during a code review. The code seems careful and defensive because nobody wants to build a system that gives up too easily. But in reality, true resilience isn't about refusing to give up. It's about refusing to let a small failure turn into a massive one. This doesn't mean you should never use retries. They are great when a fault is brief, random, and cheap to test again. A temporary network interruption or a one-off connection hiccup fits that pattern perfectly. Short-bounded retries with jitter on idempotent operations are usually fine. The trouble starts when teams apply those same rules to an overloaded API, a slow database, or an identity service that is already drowning. At that point, your retry logic stops being a recovery tool and starts being synchronized harassment. Leaders need to see this clearly because the damage shows up as both instability and pure waste. Your platform starts spending more on compute, bandwidth, and queue capacity just to push the same failing work through the system over and over. While everyone thinks the system is fighting to stay alive, it is actually accelerating its own collapse. The fix starts with classification. You have to ask what kind of failure you are actually seeing. Did the dependency reject the call quickly or did it time out? Is the latency climbing for everyone? Is the response a signal to back off or is it a sign that one more try might actually work? You should only retry when there is a real data-backed reason to believe the next attempt has a better shot than the last one. If you don't have that, you need to cut it off early. Once retries start spreading damage, your job isn't persistence anymore. It's containment. Bulkhead isolation changes the system model. If retries are what spread the pressure, you need a way to stop one failing dependency from stealing resources that belong to something else. That is exactly what bulkhead isolation does. It isn't just a tuning trick or a small optimization. It is a hard rule about which parts of your system get to consume resources when everything is under stress. Most teams assume their services are already isolated because they live in different containers or different repos. They might even be managed by different teams. But that isn't real isolation if those services still share the same outbound connection limits, the same worker capacity, or the same downstream bottleneck. The architecture looks separate on a diagram, but the failure path is exactly the same. So what is a bulkhead really? It's a boundary that limits the blast radius of a failure. When one dependency struggles, the rest of the service refuses to hand over all its time and capacity to save it. If one workload spikes, another workload still has the room it needs to run. That is the shift you have to make. You stop asking how to recover a specific call and start asking what resources you are willing to let burn with it. In a .NET system, this becomes a practical design choice very quickly. If you have an HTTP client talking to a fragile external API, you give it its own limits and its own timeout policy. You might even give it its own dedicated handler settings. If one background job is processing exports while another handles payments, you cannot let them drain the same execution path without guardrails. If a specific message consumer has the potential to flood your database, you have to split it away from the flow that supports your customers. The goal here isn't elegance, it's separation under pressure. One level deeper, you realize that bulkheads don't have to map directly to services. They can map to business value instead. You can isolate by dependency so a slow search provider can't drag down your authentication service. You can isolate by capability so a heavy reporting job can't starve the checkout process. You can even isolate by tenant class so one noisy enterprise customer doesn't crowd out everyone else on the platform. You can also isolate by traffic importance to ensure user actions keep moving while sync jobs wait their turn. This is where things change because resilience stops being a generic tech concern and becomes an explicit business policy. Shared pools are usually where this whole model breaks down. A team might say their features are separate, but the requests still land in the same app instance and compete for the same outbound calls. They hit the same queue workers and fight for the same database connections the moment latency starts to rise. Separation on a diagram means very little in the real world. Under stress, the shared pool becomes the real system boundary, and everything inside that pool has the power to hurt everything else. I've seen this happen in commerce systems where checkout, profile sync, and reporting all looked independent during architecture reviews. Then one downstream dependency slowed down, which caused reporting jobs to stack up and profile updates to linger. Connection pressure climbed until checkout started missing its response targets. In that moment, nothing in the business wanted those workloads treated as equals, but the platform did it anyway because nobody drew a hard line around the resources. A better design admits something that feels a bit uncomfortable. Equal access is often the wrong rule. When your platform is healthy, broad sharing feels efficient and smart. But when the platform is stressed, that same sharing becomes a permission slip for low priority work to steal from high priority work. Architects have to choose early on what gets protected and what gets constrained. That might mean reserved consumer capacity, separate queues, or per dependency concurrency limits. You might need independent connection budgets or dedicated compute paths for revenue critical operations. You don't do this because the system is dramatic. You do it because the system needs structure when behavior gets messy. This is also where technical design turns into leadership. Product and engineering leaders have to agree on which paths deserve guaranteed room and which ones can wait or fail. If nobody makes that call, the platform will end up making it for you by accident. Bulkheads don't fix a bad dependency, but they do something much more useful. They stop that dependency from collecting unrelated victims. Once you have created that boundary, you still need a fast way to decide when a call should just stop entirely. Circuit breakers stop panic before it spreads. Isolation gives you boundaries, which is a good start, but a boundary still needs a decision rule to actually function. If a dependency keeps failing and your service keeps trying to talk to it, you have only slowed the damage instead of stopping it. That is the job of a circuit breaker. It watches a dependency, judges its recent behavior, and changes how calls flow based on what it sees in real time. Think of it less like error handling and more like traffic control. When the dependency behaves normally, the breaker stays closed and requests pass through without any friction. When failures cross a threshold in a given window, the breaker opens and stops sending more work for a while to let the system breathe. After that pause, it shifts into a limited test mode where a few calls get through to see if things have improved. If the dependency responds well enough, normal flow resumes, but if not, the breaker opens again and the cycle repeats. The pattern is simple: allow, stop, test, and recover. That sounds obvious, but most teams still run the opposite model in their production environments. They keep every call alive until a timeout finally proves the dependency is sick, which means every caller learns the same lesson separately while holding onto resources the whole time. A breaker turns that painful process into shared memory for the entire service. Once enough evidence shows the dependency is failing, the platform stops pretending the next 100 calls deserve a full wait and just cuts them off. That fast rejection matters more than you might think. A quick failure is annoying for a user, but a slow failure is expensive for the platform and everyone using it. If the service can reject a request in a few milliseconds instead of waiting seconds for another doomed outbound call, it saves thread time, socket lifetime, and queue pressure. The user might get a fallback or a partial response, or maybe they just get a clean error message, but the service itself stays capable of handling other work. And that is the trade you are making. You are not promising everybody a full answer all the time because you are choosing platform survival over graceful denial. In most incidents, that is the right choice to make for the health of the system. Users can usually tolerate a narrow feature failure far better than a broad system stall that locks up the entire interface. The tricky part sits in the tuning of these thresholds. If the threshold is too loose, the breaker reacts late, and the service keeps wasting time on bad calls that were never going to succeed. If the threshold is too tight, it opens on minor noise and blocks healthy traffic that should have gone through. The sample window matters just as much because a short window catches sharp failures fast, but can flap if traffic is uneven. A long window smooths out the noise, but it might respond too slowly when a dependency drops hard and needs immediate isolation. This is why one breaker for everything usually fails to solve the problem. Dependencies behave differently, and an internal cache API is not the same as a third-party payment gateway. A token service is not the same as a reporting endpoint, so they deserve different thresholds, different timeout budgets, and different fallback rules. When teams attach one generic policy across all outbound calls, they flatten those differences and lose control at the exact moment they need it most. In .NET, this means you should scope policies per client and per dependency path instead of using one blanket setting. Your HTTP client for identity should carry rules that match identity, and your client for search should carry rules that match search. Then you compose the pieces in the right order by starting with a timeout, adding a breaker, and finishing with a fallback where the contract allows it. The order shapes the behavior, and if you get it wrong, the policy stack will just fight itself. One more thing trips teams up when they implement these patterns. They open the breaker, but the rest of the platform still rewards unsafe behavior by calling too aggressively from upstream. Queues keep feeding work without any back pressure, and product flows assume every dependency deserves a live round trip every single time. The breaker helps a lot, but if the wider system treats degraded mode as an accident instead of a feature, pressure will just find another route to break things. Built for controlled degradation, not perfect uptime, the next shift in thinking is actually bigger than the code itself. A lot of cloud teams still chase perfect uptime as if every single feature deserves the same level of promise. That sounds disciplined and customer-focused on paper, but under stress, that model turns every feature into a shared liability. The platform keeps spending scarce capacity on work that does not need to survive the incident, and once that happens, low-value requests start competing with the paths that actually keep the business moving. A healthier model starts with service quality tiers. Not everything needs the same behavior. When the system is under pressure and resources are running low, some flows must keep working even in a thinner form, like authentication, checkout, or critical case creation. These are the paths where delay or failure immediately hits revenue and trust, so they need protection first, because the business loses the fastest when they stop. Other flows can bend without breaking the whole experience. Recommendations can pause for a few minutes, and exports can sit in a queue until the pressure drops. Search enrichment can disappear for a while, and analytics pipelines can fall behind without hurting the person currently trying to pay. A user usually tolerates those small gaps if the main task still completes. And in fact, most users will not even notice a degraded feature if the path they came for stays responsive. They only notice when the whole product drags and becomes unusable. That means resilience design needs a more honest question from the start. Instead of asking how to keep everything alive, you should ask what keeps mattering during a moment of extreme stress. Once you answer that, your architecture choices get much cleaner and easier to manage. You can return partial responses instead of blocking on optional data that might not even be necessary. You can serve stale reads where freshness is not worth a live dependency call, or you can buffer non-urgent work into queues to process later. You can even keep cached claims for a short window if the identity lookup path is struggling and the risk fits the use case. None of that is fake availability, but it is controlled degradation that protects the core transaction instead of collapsing around optional behavior. This needs product input instead of just platform input. Engineers can build fallback paths, but they should not be the ones guessing which business promises can soften during an incident. Product leaders need to define what good enough looks like in degraded mode, and legal or security teams might need to approve where cached data is acceptable. Operations teams need to know which delays are tolerable and which ones trigger a manual intervention. If nobody defines those limits early, the system will just invent them badly when it fails in production. I have seen teams learn this the expensive way during major outages. One customer-facing workflow stayed usable only after the platform started dropping recommendation calls and trimming response payloads when pressure rose. Users kept completing the tasks they actually came to do. And even though it looked messy internally, it felt stable enough to the outside world. That distinction matters because controlled degradation rarely looks elegant on a dashboard, but it preserves the only outcome the user actually cares about. This also changes how you review your architecture during the design phase. A design review should not stop at asking if the system scales under normal load. You need to ask what this feature does when a dependency slows down or when a breaker finally opens. Does it fail closed, return less data, or just switch to cached information? If the answer is that it waits forever and hopes for the best, you know the system is not actually ready for production. It changes how you think about SLOs as well. If every endpoint carries the same expectation, teams end up hiding business priority behind technical symmetry. It is much better to define separate goals for critical parts and softer goals for optional capabilities so you can fund the architecture accordingly. Cloud cost discussions improve too because you are no longer buying broad redundancy for features that can degrade safely without hurting the bottom line. Once you work this way, resilience stops being a vague promise of uninterrupted service. It becomes a concrete plan for which parts of the system keep working when the rest of the world needs to let go. If you want more of this kind of structural thinking, follow me, Mirko Peters, on LinkedIn and share this with your team if you are dealing with these problems right now. Operationalize resilience in net teams. Resilience fails when it lives as a few helper classes inside one isolated team, but in reality, what happens is much simpler. One team adds poly, another team copies a timeout value from a random blog post. A third team wraps everything in retries because they're afraid of user-visible failure. Every service looks protected in isolation, but the platform as a whole has no shared rule for how dependencies behave under stress. That isn't architecture, that's just drift with good intentions. The fix starts with standards that are specific enough to actually enforce. For every outbound dependency, you need to define 5 things: the timeout, the retry rule, the breaker rule, the fallback behavior, the isolation boundary. Write them down and version them. If a service calls identity, storage, payments, or search, the team must know exactly how long it waits and when it stops. They need to know what it returns instead of an error and which resources are fenced off from the rest of the app. If those rules aren't written anywhere, the real policy is just whatever shipped last. Then you have to assign ownership by the dependency, not just by the service. Incidents turn messy because nobody owns the full behavior of the call path. The product team owns the feature. The platform team owns the cluster. Another team owns the shared service. But nobody owns the failure mode between them. That gap is where toxic behavior survives. Somebody needs to decide what acceptable pain looks like when a dependency degrades. And that decision cannot wait for the incident bridge. Testing has to follow the same model. Don't wait for production to reveal the bad path. Slow the dependency on purpose. Force timeouts, open breakers and staging. Cut a non-critical API and watch what spills over. You aren't testing whether the code is elegant. You're testing whether the business keeps the right things alive when a dependency turns unreliable. That is a very different exercise, and it changes what teams pay attention to. The signals matter too. Most dashboards still center on uptime, CPU, and request count. Those are useful, but they're incomplete. You need to see saturation, queue depth, timeout rates, open circuit counts. These metrics show when the service is still reachable but already losing capacity, and that is usually the moment that matters most. Architecture reviews need a different lens as well. Stop rewarding neat diagrams and start asking about the blast radius. Which dependency can block this path? Which pool is shared? Which caller keeps sending work after the downstream side is already hurting? The cleaner the answers, the safer the system. And this lands outside engineering too, because failure budgets and degraded modes are business decisions with technical consequences. So that's the shift. Stop treating resilience like smarter exception handling. Start treating it like designed containment inside the platform. This week, pick one critical NEAT service. Map every outbound dependency, mark every shared pool, every retry chain, and every place where one slow call can spread. Then add one hard timeout, one scoped circuit breaker, one real isolation boundary. If this changed how you judge microservice health, follow me, Mirko Peters, on LinkedIn. And if you want more of this, leave a review. It helps more people find it.